All right, so this is lecture 11, and this is the last lecture before you don't have to read anything for the midterms. In the sense, this class is included as part of the midterms as well as the third quiz, which will be on Thursday. So again, announcement is that we have a office hour tomorrow at 1 p.m. That's every Wednesday, and I think TA office hour is after that. We can discuss about the homework force or any question you may have or related to project. A couple of more due dates. Quiz 3 again will be out on Thursday evening and it will be due on Friday. So this quiz will be based on lecture number 8, 9, 10, 11. 11 is this particular class. And so all the things that is in the midterms is up to lecture slide number 11. So what we are going to cover next week is not part of the midterms or quiz. And so this quiz will give you final, all the short question you may need to know for the short question in the exams, midterms exam. Project introduction is due on Friday, which basically what I expect is you write what is your topic and write a little bit literature review. So you have at least read some articles, research articles or report so that you know how those introductions are written. So I just want you guys to give it a try because we'll give you feedback. There is no loss of credits for trying. So whatever you submit, this is your way to get feedbacks and improve those. So that's why you enforce this more like a submissions. Homework 4 is due on this Friday. And I just want to tell you guys ahead of time, there is no extension in homework 7. Homework 4, the reason is we said to release the solution right after when it's due, because I know this is part of the midterms. I want you guys to start looking at the solutions. And second reason is homework 4 is basically you put the equations and plug the value, you get the answer. This is not very difficult questions like other homework. So you have set equations. As long as you identify the variables, you can put the solutions and I'll put those values, get the answers. It should not take longer. So that's why another reason you should try from now. You still have 3 to 4 days. So make sure that you finish on time. Because once the solution is out, we'll not accept your solutions, whether you saw it or not. TA has already worked out the solution for homework 4, and I'm going to release homework 1, 2, 3 solution tonight, so that you see those solutions and match with your answers. Graders are grading your homework, so you should also see those once they release it. But at least you should know the solution for your midterms. Again, midterms is open book, so you have all the solution, everything with you while you are working on it. And the again, just want to say that we need your introductions. You have a title, you have a short abstract which you wrote before about the scope, and based on that, we'll evaluate how your introduction is written. We'll give you feedback, and you are going to submit it back. Okay, so that's how you get 10%. It's not just what you write. What you write, you submit to us. You don't lose any point or you don't gain anything. But once we give you feedback, then you resubmit. That way we know that you address those issues. This is the way you can go after another. By the final week, you don't have much to do. All right, so midterms is next week, Thursday. We release that during the class. There is no class. That means I expect that you can take the midterms during class if you want to, because that's not. But you can take on Friday too, because it's not due until Friday midnight, and it's the entire time. So once I release it, you have all the times to work on it. But doesn't mean that I expect you to take that long. Okay, the exams are set for 3 hour maximum. That means you just need 3 hour window to work on it. Okay. Example midterm. So I released that last class. Check out the question so that you know what kind of question to expect. Um, and then we can solve those questions on next Thursday so that you get those understanding. Usually, everybody does well in the short questions because you have already take the quiz, you know the concept. The questions that you may have difficulty to some extent is the mass balance question because you will ask the same question a different way. You just have to know what is input output. So that's why you have to solve more examples. So check those two questions on the midterm so that way you can have some idea. All right, so this is the last class, as I said, about related to midterms. And one of the questions in this class is in your homework, 4 questions. So we'll solve some example here so that you know how to solve those. Okay, so this is also incidentally very one of the most popular green infrastructures design, which is in um, either rain gardens or bioinfiltration system or bioretention system. These are called different ways, but they all work in a similar process. So you are going to basically any green infrastructure where there is infiltration, you will learn about that, at least in filter media. So infiltration-based green infrastructures are very popular because they can remove pollutant more efficiently. But doesn't mean that you can apply infiltration-based green infrastructure everywhere. The location where you cannot apply this is where the soil itself doesn't have high infiltrations. The reason is it rely on water to move through the entire filter layer. Then that water, filtered water, has to go somewhere. The natural soil do not have any infiltration capacity. Then where that water will go? They have nowhere to go. That means there will be no more infiltrations once it's all soaked in water. So that means infiltration-based green infrastructure should have the condition is soil should have high K to recharge groundwater. Or if you don't have this one, so yes, then apply. If if no, then use under drain so that you can discharge those water to storm drain. But under drain is expensive because you have to design some extra infrastructures for that. Wherever you can't apply under drain, you cannot use infiltration-based green infrastructures. So this is just one example. So all it means that you replace the soil with some amount of filter media. Traditionally, it is sand and some amount, very small fraction of soil. The reason we use sand is so that you can infiltrate water very quickly. And then compost is used to support plants above, and also compost has some capacity to remove pollutants. As you see at the very bottom, you see those the arrow mark indicates that the infiltrated water getting into groundwater. But wherever you don't have that soil doesn't have that capacity, you will create a under drain, and then that water will go to some pipe somewhere you can easily discharge. So one of the examples, rain garden, you can watch this YouTube video where they how they design it. This is something you can do in the single family home. Basically, the reason is simple. You just replace this soil with sand and compost, add some layer or liner if you don't want the infiltration to occur inside the ground, um, or channel it to somewhere else. And then usually this is a little bit far from the home because um, you don't want to destroy the foundation of soil, foundation of your home. So it's a little far from 10 feet, at least 5 to 10 feet far from the wall. And what usually happens is all the water that comes on the roof, you will channel that water from that rooftop to these locations. That way you don't have to irrigate. So you can see that in many places. Basically, you can create your own garden this way. There are some other way to, you can check structural, which is basically on the roadside. You see this location with plants, and here it is too. So you usually water goes in, um, and there are some tree boxes, but those are not necessarily filter media that much. Um, so for instance, here water goes in here, and there are other locations like in um, water comes here. So there are curb cut, so the water goes in. So you can see that many system has this particular features. But just from looking from up, you can't say whether there is an under drain or not. And 90% of them do not have any under drain. That means it's assumed that this is for either retention of water for temporarily if there is no infiltration capacity, or if it is there is some infiltration capacity, it will get into ground. So there are different design components that you can design, but these are the four things you have to think of. Very first one is hydraulic control. Hydraulic control means how you channel all the water uh, into the into the green this rain garden. So think of how water moves. So this is hydraulic control. So how water is fed into the system. And there are a couple of things you change. Is basically you can see there are some kind of grass strip or some rocks. The idea of having those things are to slow down the water speed, slow down the speed. Why you need to slow down the speed? Because you want to use them as a sediment trap. If you don't use them, all the sediments will get into this bioinfiltration system and it will clog the system. So that's why there is a sediment pre-treatments. And this also slow down the water. That means you have less erosion of the actual bioinfiltration system place. So that's hydraulic control. The second is vegetation. That's here. So that's one. The next one is vegetation. So that's basically plant uptake of pollutants. There are different reasons for why you need vegetation. First is plant uptake. Number two, those plants are also helpful uh, to prevent erosion of the soil filter media itself. Because if you have plants as root, they hold on to that soil strongly. So whenever there's a water flow, it doesn't uh, erode. So that's prevent erosion. And then there are a third benefit is if you have plants, what they do is they also increase the infiltration capacity of the soil. Because if you see these roots, the roots dies and the new root grow. Everywhere there are root channel, they create also the flow path, or it's like a highly permeable layer where water can move through those wherever roots were. So it can remain high, or hydraulic conductivity remain high if you have plants. The third one, which is a filter media, which is this. This is the third one. Is this is one. This is three. Filter media is the heart of this design, where you remove most of the pollutants. So usually, as I said, their goal is to increase infiltrations, because you want water to move as soon as possible so that it doesn't pond. Usually 48 hours time. You don't want to have ponding for more than 48 hours. And then number two, the goal is to remove pollutants. So this is where you can mix different amount of materials so that you can remove pollutants. The fourth one, which is how you let the stormwater goes out of the system, is a raised outlet. So usually in this case, most of the, as you see from aroma, things are moving, or they are infiltrations or exfiltrations if it is side. But sometimes you have this, you have a liner that prevent any kind of water going in, but you can have a raised outlet. So basically, there is a pipe that you can raise it all the way up so that water exit from the system a little bit higher than the bottom place. What it does, it creates this submerged zone, or this is called submerged zone. The reason is that outlet is up to here. And so the reason behind it is you store more water. If you store more water, then there is a chance that there will be more infiltration if there is no layer, because there is more water pressure above it. The head is higher. And second, you also create certain kind of anoxic zone. If you pond some places for a long time, oxygen will deplete, because microbe is going to decompose many organics inside the systems and consume all the oxygen in water. Because it's not exposed to atmosphere readily, the oxygen is not replenished as quickly. So that's why there are sometimes intentionally want to do that to remove some pollutants which are removed only in anaerobic conditions. So raised outlets, the benefit is it is increase infiltrations because the heading is high. Then remove some pollutants. Basically, let's say nitrate. Anything that require anoxic conditions. Nitrate is one which is require anaerobic microbial community. So these components that I just discussed is all written here. So you can read those. I think I gave a handout. If not, I'll upload it. So you can read that if you want to know more about different layers. For instance, certain things I didn't discuss is a transition layer, which is basically coarse sand, because you want to put the filter media and you don't want the filter media to wash up from the system. So you put a sand layer, which goal is just letting water move as quickly as possible away from the filter media without having the filter media pass through the system. And then we have drainage layer, which goal is just to install the pipe and make sure there are big gravels there so that there is no resistance for water to flow. Okay, so usually you put gravels and there are some are fine aggregates sometimes. Again, why we use this kind of system, why it is popular, there are many reasons. Number one, it requires less space, because you can treat a lot of water through vertical. You don't have to have very wide areas. And space is limited in most of the urban areas. So that's why this is something preferred. And this is also attractive landscape design. You have plants, you can put a lot of different plants. So it looks good. And also it has a lot of flexible design. As you see, there are so many things you can control. You can add different filter media. You can do all those other things. You are also, this requires maintenance a little bit, but not, if you are at home, it's like as less as garden maintenance. And it create other ecosystem habitats. So that means it provides some more value. Just know that if you have a rain garden and it doesn't drain quickly, it creates mosquitoes. So that's one thing you have to think of when you design this. So when it start clogging, that's the time you have to remove the top layer. So again, it has many different. These are all the design things that discussed. And we discuss about physical, chemical, biological process early in this class. I'm just going to highlight which are important here now. So as I said, there are many processes here. There are like physical, chemicals, biological processes. So if I ask you what kind of physical process here, the very first thing is any sediments can settle. Okay, so that means that's the first process, sedimentations. Just by large particles settle there. Then there are second process is the plant. So this is one. Then this is second. Because there are plants, those plants will uptake lots of pollutants. So that's why plant uptake is This is mostly biological process, right? Um, so that's the second process. We are going from top to bottom. Then the third one is in filter media. So this is basically um, adsorptions. They can stick with the filter media. They can also degrade in using the microbial community inside the root systems or degradations or any other form. So this is basically physical, both physiochemical or biological. Because another thing I can write is training. We discussed this. Training means if your filter size is very small, filter media, the particles, very fine particles can filter out because the pore size are so small that they can pass through. So as you can see, straining is physical process, adsorption is physical, chemical, both. Degradation is biological process. So all these things can happen in that filter layer. Then the last one over here is basically things are moving out of the system. So that's number one is just the draining or transferring water. So again, these are all how to describe those: hydraulic conductivity, sedimentation. You already solved problems. Plant uptake. This is mostly on transpirations. You don't really use an equation in this class, but just know that they exist. Adsorption, degradations, you already know to some extent. Straining, we already have those equations. So again, I'm just putting everything here so that you know which process are. And here in these pictures, I just put which process are important for different types of pollutants. For instance, if you see nitrogen removal is done by many different processes. Mostly it's a biological process. But if you have particulate nitrogen, which is leaves or decomposed materials, it has nitrogen and nutrients and carbons. And they can be removed by sedimentation. But once it's a dissolved form, it's mostly biological process. Phosphorus is very easy to precipitate. So it's mostly the written as phosphate. Nitrogen is mostly nitrate, ammonium. There are many forms, but these two are most common, dissolved form. Then organic nitrogen, organic. Um, you have also organic phosphorus. Basically, DNA is organic phosphorus because it has phosphate, but it's organic because part of the organic molecules. And you have also particulate nitrogen or total nitrogen. Okay, so these different process can remove by different ways. Phosphorus, as I said, it has 3 minus charge, so that's why it's very easy to adsorb into substance. That's why you see that adsorption is much more important here. So by the way, these are all the if you go from higher, it's like this is most important and the next is less important. And physical filtration is very important for phosphate because bind with sediment itself. So if you remove sediments, those particulates, you remove lots of phosphate. And then phosphate it can also be assimilated by plants and microorganisms. Then you have heavy metals. Heavy metals are mostly removed by adsorption because they stick with materials, and also heavy metals are not degraded, right? So they can be you can degrade atom because it's the elemental form. So what it does, it transforms to one form to another. So means let's say you have a iron, you can transform to iron hydroxide. So what it does, it basically changing pH, it will precipitate irons. So same thing for many metals, it will be either precipitate or adsorption or uptake by plant itself. Whereas pathogens, they can be degraded or die. That's one way. They can be filtered out because they have size, specific size, um, or they can be adsorbed on the filter media. Then you have organic pollutants. Those are mostly adsorption and biodegradations because they can be used as a food for the microorganism, or it can be also stick with the compost or activated carbons or biochar. So when you design this thing, you should think of all that, right? So in your projects, this is something you will think of. Physical process, again, we discussed this already, so I don't need to write it, but I just want to talk a little bit about the design that you want to control this process. So how do you control filtrations? Filtrations is basically, or infiltrations. Filtration means removing large particles by straining, or it's like you're filtering particulate substance from things. So usually you design, implication is you control that by particle size, particle or grain size. So if you have filter media, if you have, let's say, these big particles, you are going to most likely, these big particles will be filtered out. But if you have very small particles, they will they will come out here. But this is, so this is blocked. Okay, so particle size is one way to control it. And if you think of infiltration, how quickly you need for water to move, the standard design is you should aim for 10 inch per hour, 10 inch per hour, or another way to say is 25, nearly 10 inch is roughly 25 centimeters, 25.4 centimeter per hour. Definitely around 5 inch minimum. Okay. Another is 5 inch, so it's 5 to 10 inch per hour. That's the infiltration you have to use. For that to use, that's the reason most of the soil has very small flow rate, less than zero point 0.5 inch per hour or something. So that's why you can't apply any soil. That's the reason you put lots of sand here. So usually sand content, so you put sand. Sand has 10 times this capacity, 10 or 100 times more infiltration capacity than what is required. So that's why you put at least 70% sand. The reason you don't use 100% sand is because you can't remove much pollutants. So you put 70% sand to control the hydraulic conductivity, and then 30% you add compost or some mixture of a little bit soil and compost or mulch, which has organic to support the plants as well as helps the microbe degrade the pollutants. And then 30% is typically other amendments, organic amendment. So I say 70%, that's not necessarily fixed, it can be more, even 85% some places. So just know that the reason for sand is increasing hydraulic conductivity, which is a physical process. The reason you don't want to use smaller particles is because if you use smaller particles, it's going to start clogging because of filtration of removal of the fine particulates. So this y-axis, this graph you see over here, that's our study done in our own lab, where one of the master student, what he did is he packed sand with different amount of biochar or different size of the biochar. The reason is if you add those biochar with different size, it will clog faster based on what the size is. So C just measure the hydraulic conductivity. Initially, that's like very high, like for instance here. And when you use large biochar, and they decrease at certain rate. And when you the reason the decrease is, by the way, because they are adding a lot of suspended sediment in stormwater. So if you calculate how much amount of suspended sediments is present in stormwater, based on volume of stormwater is being added or infiltrated to the system, you can calculate how much sediment has been already added to the system. And those sediments will start clogging the pores. That's why the hydraulic conductivity decreased. And so what she did is she basically predict that change in hydraulic conductivity with initial hydraulic conductivity by just knowing what's the size of the filter media. So all you can see over here, the this line is below the other lines, which means that uh, it um, it log much faster because as you can see over here, this is a low hydraulic conductivity and this correspond to the small biochar. What you learn here is that if you apply very small size of the biochars or being fanned, it log much faster as well as um, it's the hydraulic conductivity is very low. So that's the reason a lot of times people apply large particle size. So now question is how you're going to minimize clogging. Well, you can minimize clogging by just adding different amount of large size biochar or large size amendment, or you can just scrape some of the sediments that accumulate on the surface because usually it clog on the very surface, top surface, before they even goes down. In this equation, as you see, the y-axis is this. So if you use that linear equation, uh, you will get k equal to k0 e to the power minus whatever the sediment loading rate. Let's say sediment loading rate is L. Uh, that will be, and then slope is R. That will be RL. Okay, and this R is, if you see this slope, is a function of the smallest size, or D10 means a 10% passing, the small size range of the filter media. So what he found is K0 e to the power minus, there is a slope here, so that's basically R equal to alpha times D10 L. So why this is important? It says that if you use any kind of filter media, if you know what's the initial hydraulic conductivity, you can predict how long before it start falling, it reach a certain value where it will not infiltrate enough water for you. And based on the filter media size, the D10 of the filter media that you packed, and the how much amount of sediments loading or amount of sediments that accumulate in the system, which is basically stormwater property. So this is stormwater characteristic and this is filter media. Okay, so these are,
Professor,
yes.
what is alpha in that equation?
So alpha is the slope here, this. So all it means is this R value is alpha times D10. I mean,
Okay, thank you.
there is some value here, other little things, but this is just the. Okay, so this is just, by the way, it's just one equation. You can predict clogging in the real world, if you know. Okay, so now that we have covered some fundamental questions, let's see if we understand the quiz. This will be similar quiz on your following quiz in Thursday. If the stormwater harvesting or direct use is required, which of the following design feature you must add to bioinfiltration system? So stormwater harvesting means you want to collect the stormwater without having this to um, get into um, yeah, direct use is required. Yeah.
Professor,
Yeah.
so I just wanted to confirm with you. So the midterm itself, we technically have all 24 hours, but you expect that it wouldn't take longer than 3 hours, but we have the 24 hours if we
Yeah.
need it.
Yeah.
Okay.
And I don't set the limit like quiz. Like once you open, you have certain hour. But in this midterms, I don't set the limit.
Okay. And then where the midterm will just be like a CCLE quiz format.
No, it has long question like homework as well as quiz.
Oh, I meant like, how will we receive the midterm?
Oh, you know the question through Gradescope and you write on your own page and scan it and upload it.
Okay, so we can like download a PDF from
Yes.
grade school before
Yeah.
re-uploading it. Okay.
Yeah. I mean, you can download or you don't have to. You just write question 1A. You don't have to write the question also. Just think of your homework. How you upload is the same way. All right. So I'm going to end the poll because it's lying there. Which of the following feature you must add to the filtration system? So I think this question, there are a lot of different things. Let's see the elimination of wrong answer. Um, if you don't have outlet, how are you going to collect or direct use it? You cannot collect the stormwater. So that means, this cannot be answered. Okay. Plants. Does plant really help you collect water? It doesn't really matter whether you have plants or not. All plant does is remove pollutants. There's nothing to the collections of direct use or all that. So now you have two other options. One of those two will be the answer. Increase in height of filter layers, liner to prevent exfiltrations. Increase in height of filter layer will just make you remove pollutants. It doesn't have anything, it's nothing to do with a collection of stormwater harvesting. But if you don't put liner to prevent exfiltration, you lose that water. You cannot collect it, right? So that's the reason um, the answer is liner to prevent exfiltrations, because exfiltration means loss of water. You do not have that water to reuse. Okay. All right, that's good. One more question. Which design feature will not be affected if you were to increase the volume of stormwater treatments? So your goal is to collect more stormwater and treat more stormwater. But which of the design will not affect that? So it's a negative question, not affect the. So if you increase ponding depth, is this going to increase the stormwater capture or treatments? If you increase filtration layer depth, is this going to increase or decrease width of last one is transition layer depth? Okay, you have 20, let's see, 20 more seconds to answer. All right, I'm going to end the poll. Let's see. So it says which one is wrong. So let's look at the elimination way. Which of the design feature, what happened to the, why I cannot see the screen? Okay, now I see the screen. Which design feature will not be affected if you are not to increase the volume? So as you see ponding depth, if you increase the ponding depth, you are already capturing more water, right? So that you can't have that answer because this is going to affect the volume. If you increase filter layer, that's where most of the waters are stuck, slowly moving. So that technically will not, it will increase the amount of water being treated. If you increase the width of biofiltration system, this width, that also increase the amount of volume you can capture. The last one, transition layer. Transition layer doesn't really do anything. It just let water moves from like it's just the very fast moving water. So if you increase that one, it's just you are just storing more water a little bit, but you are also losing that space from the filter there. So you're not treating those. So that's why the right answer would be transition layer depth. Okay. Width of infiltration system is basically think of this or this. Either way you increase any of these, it's going to increase the amount of water that captured. Filter layer depth is related to how much water is being treated, right? Because if you that's treating that water. All right, so that's in between what we just discussed, and this is the process that you already learned in CEE153. I'll just go through it quickly. If you want to know more, you can also watch that. But you should know enough here to solve the problem. So as you see, the pollutants move through here, they will stick around in the filter media. So that is called adsorption. Okay, and how do you predict that? So that's based on these equations. So what it says is if your stormwater has certain pollutant concentrations, after it adsorbs, so whatever the initial, let's say this is C0 is initial concentrations. So imagine this is a filter. I'm just creating a mass balance. So this is filter media and your water is coming, what stormwater is coming in. This is the C0. And then as it moves through the system, it becomes adsorbed. When it absorbs, the remaining amount of pollutants will leave the system. So that's the C. So C is the effluent concentration. So that means it's after adsorption occur. So this is concentration in effluent. So something happened here. Concentration in effluent. I'm talking about contaminant concentrations, right? So now question is how much of that, because your goal is to make this C as small as possible. That only way you can decrease it by having more pollutant adsorb on the system. So how do you know how much, what's the absorption capacity? That's basically KD. Okay, so KD means if you have certain concentration in water, stormwater, the amount of pollutant that can adsorb on that filter media, which is concentration in this is adsorbed concentrations. So Q is basically concentration of pollutant, a mass of pollutant adsorbed divided by mass of filter media. Okay, so weight of the filter media. So that's why the concentration is usually milligram of pollutant per gram or kg of filter media. Okay, that's the unit roughly people use. Milligram pollutant by kg of filter media. Whereas concentration, the unit is going to be milligram of pollutants divided by liter of stormwater. Okay, so pollutants by. So that what it says is that amount of pollutant adsorbed in a system is directly proportional to the concentration in water. And that KD is something that you learn is a function of the contaminant property as well as the filter media properties. Mostly we are talking about um, um, for organic carbons or organic pollutants. They are sticking with organic pollutants or organic filter media. So that KD you can break into two things. It's fraction of organic carbon, which is written here. This is FOC is organic carbon fractions. Okay, that means now if you burn that entire filter media, all the organic will burn. If you take the weight before and after burning, the difference is the amount of organic is present. So that's a no unit. That's just a ratio. It will be 1% or typical filter media in biofilters. You need to have 20 to 30%, 20 to 80% organic in that filter media. For instance, biochar, when you add it, biochar has 80% organic carbons. If you think of compost, it has typically 55% carbon. So you add this high organic substance materials in the system so that the net organic fraction of the entire filter media increase to 20 to 30%. When you do that, it does have higher capacity. So that's the reason, if you see why people add this filter media, is because that FOC, just to increase that all. And KOC is basically saying how efficient this filter media is to attract the contaminants, organic contaminants. So KOC is basically partitioning or attraction of that pollutant, specific pollutant toward the any organic matter. So this is pollutant properties. And these values are given in your questions. You are not finding these. These are given. You just normally what you do is you find this value if you know these concentrations and you plug this value of KD. The KD is not given, you get it from FOC and KOC. So why it is important? Because if you know the KD, which means it absorbs the pollutants, it basically slow down the movement of pollutant through the system. As it slow down, it degrade. So the whole idea of adding this filter media is retarding the pollutants when they move through the system. And that retardation factor or retardation coefficient is basically velocity of water divided by velocity of contaminants. It's the ratio of that. It means that, let's say, if the retardation factor is equal to 1, it means that water moves as fast as pollutant move. That means there is no adsorption of pollutant in the system. So as you can see, retardation factor equal to 1 if KD equal to 0. If KD equal to 0, which means that there is no adsorption, which makes sense. Adsorption. Okay, and if RF equal to greater than 1, that means highly absorbing pollutants. All it means that the contaminant velocity is so slow that you will not see that in the effluent. Okay, so that's what you want. So now question is how you can improve that retardation factor, because that's what you need to design. So a couple of ways you can see retardation factor is not just depend on the filter media KD, it also depends on how you pack the system. If you pack it very tightly, pollutant will stick with it will find the filter media more efficiently. That means it will interact with the filter media. So that's why it depends on retardation factor depends on bulk density. Bulk density means how you packed. So this is called bulk density. Bulk density is basically mass of the filter media divided by volume where it is packed. So if it is packed very tightly, the bulk density is high. There is a negative effect of bulk density too. If you pack too much, it's not going to filter, the water itself will not going to move. If water doesn't move, then there is no pollutants. Pollutant cannot move if the water doesn't move. Because that advection is important. The movement of water is important for pollutant to pass through. And the entire system, green infrastructure, is having for stormwater to pass through, not hold into it. So that's why you don't want to have bulk density too high. So that's another way of, so that's why bulk density people don't control, this loosely packed. The other one here is porosity. All it's saying is that if you porosity depends on types of filter media you add. What it means that if you add smaller size particles, that has low porosity. Low porosity means it has a more retardation factor. But again, there is, as I said, these are hydraulic control. Bulk density or porosity is just control how slowly water moves through the system. KD is more of reactivity. Okay, so rho B by These two is more about hydraulic control. Means how slowly water moves through the system, because if it moves slowly, it has more time to react or remove the pollutants. And KD is basically reaction control. Okay, so by using those two, you can change the retardation factor more. So just know the equations, that way you can find out. Again, I already discussed about the bulk density and everything, so you know those value. Um, Design considerations is basically you you can increase bulk density by compactions, but if you increase compaction, hydraulic conductivity decreases, right? If you increase compaction, porosity decreases. Okay. By doing both, you could increase KD, but you are also um, compromising the infiltration capacity. Adsorption capacity is basically KD increases, and the only way you can do that is adding more FOC. FOC means add organic filter media. Example would be mulch, compost, biochar, activated carbons, all those things you can add. Again, this is fraction of organic carbon is important if it is organic pollutants. Not every pollutants require organic carbon. And there are some pollutants like metals, some metals, they don't really affected by organic carbon that much. They have binding sites. For instance, removal of phosphate is nothing with organic. They don't bind that well to organic. To some extent, but it's not that much. In that case, you have to add some other type materials. For instance, iron filings or zero valent irons, those will be added. There, the equation is just KD. It doesn't have this fraction of organic carbon. All right, so let's solve one example, because this is the example question you have in your in your homework number 4. But let's take a break. It's 4:57 already. You already learned every concept. Now it's all about using this concept to solve many questions. So let's take a 10-minute break. When we're back, we solve these questions. And once you solve these questions, what I'll do is I'll give you some time to discuss the homework question, which involve this particular question type of process, that we can solve that particular question in this class today. All right, so it's 4:58. Let's meet at 5:10. Let's take 12-minute or 10 to 12-minute break. Recording. All right, so we'll get back to this example at the end so that you know why it is important for the design. What we learned so far is that if pollutants move in water through the biofiltration system, it can be absorbed on the filter media, and there are equations that can predict the removal capacity or how much concentration will be at the end. But there are biological processes which is very slow. Okay, so that's those biological processes are also important for long-term degradation of those pollutants which are already absorbed. Because if you continue to absorb a lot of pollutants and those pollutants do not go anywhere, it will accumulate. Then the whole system become a source. So you don't want that. So that's why you have to make this biological system very active so that they can decompose those pollutants, particularly organic pollutants. And nutrients, they will use it for their food. So that's the reason you see those plants are there. You also add lots of organic carbon, because those organic matters release nutrients as well as carbon, which is a source of food for bacteria, fungi, and other higher organisms. And as you can see, they can also support this larger biodiversity. For instance, it will help for the earthworm to grow, and earthworm can be eaten by other organism, and then you have all these higher organism they support the food chain. So the biological process, mostly stormwater treatment or engineer focus, is a plant. Okay, so what kind of plants you will use, how to design those systems such a way that plants can be actively taking pollutants, and what kind of soil mix you should have so that there will be more microorganisms that can degrade the pollutants, and particularly fungi. This is something newer things. Before, people don't really use fungi for any purpose. This is still new for stormwater angle. So now more and more people are thinking of how to grow more fungi in the systems. And bacteria is naturally there, microorganism. You just give them more food or kind of compost or system so that they can survive. So if you see, there are some design consideration you have to do. The very first one is any biological system require water. So if you design such a way that all the water moves very quickly and there are no holding water, there is no water holding capacity, it will become very dry. And if it's a dry soil or dry filter media, no organism will survive for long. So that means the very first thing you want to do is water holding capacity. And water holding capacity is related to um, capillary of the filter media. Capillary means if you have very tiny tube, if you put in a water, the water will rise. Okay, that means in the uh, in the regular in pores, water will hold into this small fine or the gap between the fine particles. So that capillary is very important because if it hold the water, it prevent water to drain during gravity. And so if that happens, then then that means those waters are there for plants to take, okay, an organism to survive. So the way to control is particle size. You do not want to add too much sand. If you add too much sand, it will drain very easily. So that's the reason to increase water holding capacity, people add compost. Compost soak a lot of water and they keep it there. So compost is one way. You can also add biochar because biochar is very porous. Uh, it hold that water for long. And then there are other materials. So basically, you decrease the size, particle size. If you decrease particle size, water holding capacity increases. So that's the very first. And second is basically nutrients. You got to supply nutrients for those, and usually those nutrients means nitrogen, phosphorus, carbon, right? But nitrogen, phosphorus are pollutants in stormwater itself. So you don't want to add those nitrogen, phosphorus a lot because those are naturally present in stormwater. You want them to be removed from the system. So what you do is you add a lot of carbon. So carbon rich media or NP limiting. If it is NP limiting, that means any microorganism grow, they are starving for nitrogen, phosphorus, they will take it from stormwater. The third one is stress management. So what kind of different stress that could happen in the stormwater treatment system? Number one, you have a climate stress. Means you don't want things to be too dry or too it. You also don't want it to be too saturated. That's another thing. You have to maintain that water. If it's too saturated, then some bacteria will not survive because no oxygen. Um, Climate is one of the things. Another is the compactions. If you compact the soil a lot, it's going to decrease the infiltrations and it will also affect the microorganism. Uh, After compost, it says biochar. Yes. Let me write this one. Okay. So you want to decrease compaction, not too dried. And then the third one is pollutant itself. If you have too much pollutants, it will be toxic to contaminants or toxic to microorganisms. But these are designed to accumulate pollutants. So that means you have to also find a way to degrade them quickly so that they don't really create some kind of negative effect. For instance, antibiotic resistance, something that can develop in the system, because what you are doing is you are creating this system where all the normal or the natural microorganism accumulate in the system. The same place you have also antibiotics, metals, all these harmful pollutants are there. So these bacteria will be stressed very easily. They get stressed, they develop this resistance. And that's actually another type of pollutant. So you got to think of those kind of things. So resistance or biotic resistance. So these are the things you can be also part of the stress. All right, so let's see what we learn. If you want to increase nitrate removal, which layer should you increase? Ponding, filter, transition, drainage. So just to give a context, nitrate is not removed by filter directly or filtrations or adsorption. It requires you to have unsaturated submerged layer. Okay. The way it is written, it can be confusing because I see how you are responding. Obviously, filter layer will remove some because of the root uptake, but it's during the stormwater treatments, it's not going to remove a lot. The reason is nitrate uptake is a very slow process. It takes long time for nitrate to be removed. So all this filter media layer doesn't remove much. It's only removed by biological process. And biological process require that submerged layer. So whatever the layers that create that submerged layer is the things that you want to do. This is a confusing question. That's why I'm going to end the poll, but I'll share the result. This is what you guys chose. But usually what happens is you add carbon in the transition layer, that's the electron. We'll learn that in the next couple of slides. And you create a drainage outlet higher. So that means this is a submerged zone with a high carbon amount. So that's basically during the transition layer, you create that. If you added a bigger transition layer, more submerged layer, that's where nitrate will be removed by microorganisms. The answer is transition. Because during stormwater treatments, it's just the removal in the filter media. It's not, nitrate will not be removed. They are not going to stick anywhere. Okay, so now that you learned the basic, let's see how you can apply that in your project design. So I'm just going to go through one by one. So first thing you have to do, let's say you have a project. What you do is you do some pre-designed considerations, means how big this bioretention system should be. The very first thing you want to do is scale. How big this scale should be, and that depends on multiple factors, but the most important factor is the storm event, because you are going to collect water, right? So you are going to think of how much amount of runoff you are going to receive. So that's Q, runoff volume, that you calculate using CIA, or the CIA, that formula is more important now. So this is something you have to account for. What's the size of the catchment, all that factors. Okay, so that means you are looking for, so this scale depends on a function of runoff coefficient, so that's here, and area of the catchment. Okay. Then the second thing is site characteristic. Site characteristic means, what are the infiltrations? What's the soil type? So those are the things. So soil type, climate, because these things will affect what kind of design you'll have, infiltrations or exfiltrations, or you did need there are many other factors, right? And the third one is drainage or conveyance. There are the three. Drainage or conveyance means how you are going to have the outlet. Okay, so this is mostly about outlet. Now question is, what are the two choice in the outlet? Either you will not have any outlet, that all the stormwater will go inside the ground by direct infiltrations. That's only occur if the soil is highly permeable, native soil. And you will have outlet if the soil itself doesn't have much capacity, so that you can treat them and discharge it to somewhere else. So that's why it's just infiltrations or outlet to storm drainage, infiltration into ground. So that all depends on soil type, right? Then the fourth one is TMDL. If that location, whether they need any um, particular pollutants to be removed. So this is mostly on TMDL. Because if you know metals are one of the target pollutants, you have to design certain way. So that means you are looking for this will tell you what kind of filtration or filtration unit or filter media that you want. Then the last one is water reuse. Again, this is basically your outlet. If you are looking for collecting water, or you are looking for just infiltrating water. So how big this should be is based on design storm. That's where you are looking for. Is this a 100-year storm or 20-year storm? And what kind of storm event? So design storm is, in this case, in Los Angeles, you are looking for 85 percentile. Okay. So that means on 85 percentile, 100 years, 24 hours. So what does that mean? If you take at the 100-year storm event for 24 hours, you'll see different intensity distributions. You are saying that what is the maximum intensity is like that capture the 85% of storm happens in this period. Okay, so that's 85 percentile. And some places they give you just intensity. Design the storm for this 2-inch rainfall for 24 hours, or 1-inch rainfall for this many hours. So that's how you will design it. Catchment area, if you have bigger catchment area, you need bigger infiltration capacity or bigger system so that you can collect that much stormwater. So if this increase, your size would increase. If the rainfall intensity would increase, your size of the treatment system would increase. And then performance objective. Performance objective means if you are removing pollutants or not. So these are basically your design, all the depth or filter media depth, width, all that stuff. So there are some other things that you have to think of is soil properties. The reason is soil itself will determine what's the infiltration capacity. So that's one thing. So this is the very first thing you are looking for is what is the K value. K high means you don't have to have under drain. Okay, if K is low, then this will determine infiltrations or under drain. Okay, or combination of both. And the second thing, soil property, is KD, because soil itself can remove some pollutants. So if the KD is high for the soil itself, you can mix some of the soil in the system. The second thing, which is very important, is groundwater. If you have a shallow groundwater, you are creating the stormwater treatment system, you are creating a pathway for pollutant to move to groundwater. So you don't want that. So if it is shallow groundwater, what you do is add a liner to protect, add liner to protect groundwater. If it is deeper groundwater, you don't need to worry about protection. So that's one thing. And catchment characteristic, if this will determine what kind of pollutants. Okay, if you know what kind of pollutants are in the system, then you know source of pollutants. Then you know what kind of design you want to use. Right, so these are the things you will think of in your real project. So these are the things, that's why I put it here, so that you can start applying it. This is not the right spelling. So the last one is the drainage. Drainage means how quickly you move the water away from the system, right? After the treatment. So the very first thing is it is going to have overflow. So basically, if you have a system like this, stormwater come in, it will go out like this. So this is overflow. Okay, and that depends on how much. If you are accounting for overflow, then you can design certain way. You don't need that deeper layer under drain, all those things. Um, but if you need to capture and actually use it for so this is basically flowing stormwater and decreasing the peak flow. So that means you are mostly flood control. Okay, but if you have underground drainage, that means you are actually channeling some of the water from the above ground. So this is also flood control too. This is flood control, but here flood control plus this is harvesting. Because what if your area has so small amount of water that you actually want to capture them and use it in later. So this is underground drainage will help you connect that water to something underground tank. Okay, and so this is mostly in Los Angeles or other dry area. You want to harvest water. Okay, so this is usually for dry area. Then also connectivity to other waterways. Hold on, give me a second. Let me come back for a second. I smell something burning. Right, so then connectivity to the other ways means, if you want to discharge that water, stormwater, um, stormwater, once it's treated, you want to discharge it to, let's say, a lake or river. You want to ensure that these are placed in proper locations. Another last one, this is something always we consider, is the contaminants. But you have to think that many places people don't design this for contaminant removal. The reason is it's too expensive. Also, a lot of times they don't really require to remove some pollutants. What they do is they're just required to meet the flood reductions. They are saying that 90% of the stormwater is going into ground. So this is just pollutant is important increasingly because you want to harvest water and don't want pollutant to be there. So you are basically looking for land use type will determine what kind of pollutants you are going to use. And TMDL, basically whether residential or all those things are written here. Okay, so all this over here you can read and find out those. So I'm not just to give you details because that's something is required for your project based on different project type. I just want to show that where the informations are. The last one is ecological units. Ecological unit means if you have let's say you design the system so that you have number one is biodiversity. If you put all these leaves and plants, they're you don't have in Los Angeles, you don't see lots of birds and all that native native birds and other things if you don't have enough trees. So this is something we can bring those back. And one other aspect is heat island effect. If you add lots of plants, it will also help you lower the temperature, something that we didn't discuss. So that's also another ecological benefits that you have to think of. The last one, so these are the design decision that you should think of when you, again, I share this handout. If not, I'm going to put it, just see those tables so that you can decide how you can make the decision for your own site if you're using this one of those tools. So as I said, if you um, first is size. That size depends on how much stormwater you capture. So that's again depend on Q equal to CIA. So just use this function to calculate this amount of flow rate that you'll receive in that locations. And once you know these things, you can design all these other things. What's the width of the system? What are the was the hydraulic conductivity of the filter media so that that flow rate, entire flow rate will be treated. Um, and also what kind of plants you can put it there so that it has enough moisture. Other thing of the for the design is clogging. If you want to design something very wide, that means you more likely will not clog the system, because in one location might be all sediment accumulated, but it will be treated in the next locations. So that's why you want to make the size a little bigger, but no, a lot of times that's not also possible in urban area because you don't have that much size. Then you have to maintain it more and more. That means scraping the surface. So it shows about all this design feature and risk it says. So read those because it's helpful for your knowledge as well as for your project. Another thing, as I said, you don't want things to be clogged. So that's why you have to put some kind of pre-treatments which can slow down the water or it can remove some sediments. For instance, if you see here, these rocks are given. So this is your cork cut. This is the biofiltration system. When the water moves here, you want them to the velocity to be slowed down. If it only slow down if you have obstacle like this. So these are obstacle. So these are one of the pre-treatment strategy. Another is you can see here the next picture here. You see these rocks are there. This is just basically slowing down the water flow. If it doesn't slow down, what happens is all this, you will have a hole here and the erosion will happen in this corner. So that's just we discussed that. I just want to show that how it is in real world. The next one, you don't want flooding to occur. So what you do is conveyance. So as you see over here, if it is this is the area that soil filtrations, but the stormwater can get in through this channel. You can put some kind of screen so that it doesn't get clogged. So that's just the one way that you see most of the places. Another thing you can see that if it is completely, in this case, what happens is if you have stormwater coming in from all the angles, and once it becomes flooded, the erosion will start because then it will start overflowing somewhere else. So what you do here is if you have some kind of this pipe, basically there is a pipe here. So once the stormwater fill completely, all the stormwater will get into this area. So that means it's not going to flood those surrounding area. So that's the whole reason you create a short circuit over there. So this is called bypass. So all you are doing is you are protecting that surrounding area from overflowing. Okay. The last one is raised outlet. Again, the whole reason of raised outlet is denitrifications. So if you have basically you have a filter media, things are coming in here. If you do like this, water comes here outside. So there is no submerged layer. But if you have raised outlet, so I'm just going to create an alternative one. So let's say this is what you do. So that means you have always, there will be some amount of water inside it, okay, when it goes. Why it is helpful? First, number one, it helps denitrification because it creates a anoxic layer. The number two, which is very important in Los Angeles, is that it creates this natural storage of water, which will help the plants to take that water later. So that means you don't have to irrigate. So this root system will be always healthy. Okay, so root has access to water, which is very helpful for in dry conditions, dry locations. This is where you save water. That means you don't lose that water. You irrigate it, that water stays for root to take later. In fact, this is something you can see in a pot that you buy from Home Depot or other place to have any pot inside, not indoor, sometimes outdoor. You see a very small locations where there is a very little, the pot will have water coming out, but there is a storage location where they hold some amount of water so that the plants will not dry out quickly. So again, this is for one thing. And second is, so raised outlet, number one, denitrifications. It helps denitrifications. Number two, it increase the plant available water. Okay, so that means plants are healthier. The third one, because you are increasing the depth of water above it, if you have no, that means you are also increasing infiltrations. Infiltrations. This is also good for recharge of groundwater. So these three benefits you get by having the raised outlet. The only reason people don't do it is because it's expensive. That means you have dig soil and put a pipe and you are creating this extra network, which is more expensive as opposed to just dig a soil and filling sand. The last one is hydraulic. Hydraulic means whether you are going to under drain for removing water as quickly as possible, or you are doing it for any other purpose. Um, but here, if you see, there are two things you can notice here. This is by the overflow that can go in, and then you have this perforated pipe so that it can have infiltrations. But here you have raised outlet. Raised outlet. So this is raised outlet. What it does, it basically it creates the submerged layer here so that you have denitrifications. But in this place, if you see this pipe over here, that location you can vary whether here or here, and also how it is designed. If you see there are three different design here. If you have this kind of, this is just a pipe, okay? This is the pipe, water is coming out. So if this design, you are collecting all the stormwater. So this is basically, you are not any holding any water there. So this is a good for collection. So this is collection efficient. That means if you want to collect every stormwater, this is the way design you want to do. But if you want to let the some of the stormwater goes, what you do is you create here. So it will be some of the stormwater will be captured, but most of them will pass through. So that means you are here you are doing infiltrations for recharge. So if you want to do groundwater recharge as well as the some collection, you do this design. And you can also have in between design like this, where you'll have some more capture, but you have also some of the discharge. So this is a different design you can create. Again, this is not important in terms of science. This is something your engineering design, you can think of this when you design. The filter media, particle size, you know that particle size depend filter media that change the K. If you have large particle gravel, the hydraulic conductivity is high. If the particle size is smaller and smaller, the hydraulic conductivity will, particle size increase, then K would increase. If K would increase, that means your water is moving so fast that amount of time that the pollutants stay in the system will be low, or the time it takes for the pollutants to remove, or the time for the plants and other things to happen is going to be very short. So that means the pollutant efficiency or removal efficiency will decrease. So that means your hydraulic residence time would decrease. So we call that HRT. If the HRT decreases, you have less pollutants removal capacity. So if you that happen, what you do is increase the filter layer. So what you do is increase the filter layer depth, this T. If you increase filter layer depth, that means you have more chance for pollutants to stick with the soil. If you do that indirectly, then what happens is you are increasing HRT increases, your pollutant removal increases. Okay. Again, these are the things you can design. And the last thing is there are 3 different filter media in that locations. You have top layer, which is basically filter layer. So this is filter media. The only goal here is to support plants and remove pollutants. If you want to remove pollutants, you want to increase the FOC, fraction of organic carbon, or KD. And you can also decrease the particle size. So D particle size you decrease so that you have more adsorption, more surface area. So these are the couple of things you can try. For the transition layer, usually you use sand. The goal is to make sure the filter layer is not washed off and it's hold there, and also allow the water to move as quickly as possible into the drainage layer. So you put sand there. And the drainage layer, your goal is to have zero resistance. All the water has to go out very quickly. So in this case, you are putting basically pea gravel. That's much bigger size than sand. So that means it's there just as a storage. We have, I think, 2 more slides. Vegetation is a few things. First thing, you know that what kind of vegetation you want to add. Very first thing you have to think of is you don't want to add anything invasive species, because that will affect the locations, how you want to you don't want to have a negative consequence. So always look for native. And second thing, advantage of native species is that they are accumulated with the climate. So if you have a dry climate like Los Angeles and you put a plants from something very nice from New York, it's not going to survive. So you don't want to do that. It's also maybe invasive for these locations. So that's why you want to have a drought resistance plant so that you don't have to irrigate a lot. So drought resistance plant. Okay. And then you have to also have a plants that has a deeper root system, because you want the root to penetrate much deeper. That way you can remove pollutants. So your goal is to have deeper roots. Deeper roots means it can take water from very low, deep soil. So that means it can survive. And we can also remove pollutants. Remove pollutants, more pollutants, because the root is the primary mechanism they can take up. And then also it's survive in dry conditions if his root is deeper, because the soil, the water can be extremely, the top layer can be very easily dry from sunlight. And then last thing is you can also put some plants which can remove some pollutant like nitrate or heavy metals by itself. So basically hyper accumulator, because not all plant can accumulate pollutants as much as needed. So you want to put those things. there are, as I said, we discussed this. You can put line versus online or line. The only reason you want to put line is because you want to protect the groundwater. So this is something we already discussed. Outlet, no outlet, these are all, has also different cost here. So these are written here. Again, these are different conditions why liner is necessary. So I give this list here. So these are list are important for you to prepare for the quiz. I think this is all. And last thing is maintenance. Maintenance is the only maintenance we do is a clogging, because if it is once it's clogged, it's kind of system is failed. So the only reason how you can prevent this clogging is putting some kind of pre-treatment. If you can do pre-treatment, you have to scrape the top surface like a 1 inch of layer, which has accumulated the sediments and fine particles, and then you can restore some hydraulic conductivity. But if you have plants, it does help a lot. So I think we are right on time, and I promised you to go through those questions. But what I'll do is those questions we discussed in the recording in the last year. What I'm going to do is I'm going to upload that recording, so you can watch those recording and do the question. That way you know how to solve those answers. So tonight I'm going to release the solution for homework. So check those out later, and again graders will return all the graded homeworks by end of this week or early next week, so that at least you can see where you made mistake. Otherwise you can see the compare directly. Right, so that's all for this class, because we are right on time today. We don't have time to discuss the questions. So I will stop here and stop the recording.